In the mid-1960s, radio astronomy was still defining itself. Astronomers were not searching for pulsars. They were not theorizing about pulsars. The word did not exist. The field was focused on quasars, distant radio sources that appeared unusually energetic and poorly understood. Understanding quasars required new instruments. Existing radio telescopes were too slow to capture rapid variations in signal strength. What was needed was a telescope that could detect brief, repeating radio events over large areas of sky. At the University of Cambridge, such an instrument was built. It was not elegant. It was large, experimental, and physically exhausting to maintain. The telescope covered several acres. It consisted of thousands of wooden posts and miles of wire arranged in a fixed pattern. Unlike steerable dishes, this telescope relied on Earth's rotation to scan the sky. Building it required manual labor. Graduate students participated directly. This included Jocelyn Bell Burnell, who was working toward her Ph.D. under the supervision of Antony Hewish. Hewish designed the telescope and led the research program. Bell's responsibilities included helping to assemble the array and then monitoring its output once it became operational. This output did not arrive as numbers on a screen. It arrived as paper charts. The telescope produced continuous streams of chart paper. Each strip recorded fluctuations in radio signal intensity over time. These charts accumulated rapidly. Bell reviewed them by hand. This meant hours of visual scanning, learning how the instrument behaved, learning what ordinary noise looked like, and learning which irregularities could be ignored. Most anomalies were interference, electrical equipment, aircraft, weather, mechanical vibration. Distinguishing meaningful signals from noise required familiarity with the instrument that only constant exposure could provide. Bell developed that familiarity. In 1967, Bell noticed something that did not fit known patterns. A small, repeating feature appeared in the data. It was not dramatic. It did not jump off the page. It looked like scruff, a term used to describe irregular signal markings, but Bell noticed specific properties. The signal repeated at a fixed interval, approximately once every 1.3 seconds. It appeared consistently at the same position in the sky, and it followed sidereal time rather than solar time. This last point was critical. Sidereal time tracks Earth's rotation relative to the stars, not the sun. Signals that follow sidereal time are almost always astronomical. Signals that follow solar time are usually caused by Earth-based interference. Bell recognized this distinction. She marked the signal. She tracked it. She checked whether it appeared again. It did. Bell then adjusted the telescope settings to test whether the signal persisted under different conditions. She verified that it was not a malfunction. She checked whether it appeared at other frequencies. She confirmed that it was stable. This process took time. There was no single moment of discovery. There was a sequence of confirmations. The signal's regularity was unlike anything previously observed. At one point, the precision of the pulses led the research team to briefly consider whether the source could be artificial. They labeled the signal LGM1, shorthand for Little Green Men. This was not a formal hypothesis. It was an acknowledgement that existing astrophysical explanations did not apply. The situation changed when Bell identified additional signals with similar properties. Bell found more repeating sources. They came from different locations in the sky. They shared the same basic characteristics. This ruled out a single artificial transmitter. It also ruled out a local instrumental issue. A new class of astronomical object was required. The interpretation that emerged was that these signals came from neutron stars. Neutron stars are the collapsed cores of massive stars that have undergone supernova explosions. They are extremely dense, with masses comparable to the Sun compressed into a sphere roughly 20 kilometers across. Because of conservation of angular momentum, neutron stars rotate rapidly. If such a star emits a focused beam of radio waves, that beam sweeps through space as the star rotates. When the beam crosses Earth, it produces a detectable pulse. This explained the regularity. The objects were named pulsars. The discovery was published in 1968. The paper listed several authors. Hewish was listed first, reflecting his role as project leader and telescope designer. Bell was listed second, reflecting her role in identifying and analyzing the signals. This ordering followed standard academic conventions. The paper attracted immediate attention. Pulsars became a major focus of astrophysical research. They provided the first direct observational evidence of neutron stars and allowed scientists to study extreme gravitational and magnetic environments. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars. The recipients were Antony Hewish and Martin Ryle. Jocelyn Bell Burnell was not included. This decision followed a pattern that was already established. Nobel Prizes are typically awarded to senior scientists. The committees emphasize leadership, experimental design, and conceptual framing. Graduate students are rarely included, even when their work is essential to the discovery. This approach has been applied consistently across many fields. In this case, Hewish was credited with designing the experiment and directing the research program. Bell's role as the observer who identified the signal was acknowledged, but not rewarded at the Nobel level. Bell has addressed this outcome many times. She has stated that she understands how the decision was made, given the norms of the period. She has emphasized that scientific research is collaborative and hierarchical, and that recognition does not always align with individual effort. After completing her PhD, Bell continued her career in astrophysics. She held academic positions at multiple institutions. She worked in gamma-ray astronomy and other areas. She became a leader within the scientific community. Bell later served as president of the Royal Astronomical Society and as president of the Institute of Physics. Her role in the discovery of pulsars became widely recognized in textbooks, lectures, and historical accounts. Today, she is consistently credited as the person who first identified the pulsar signals. In 2018, Bell received the Breakthrough Prize in Fundamental Physics. The award included $3 million in prize money. Bell chose to use the funds to establish scholarships for students from underrepresented backgrounds in physics. This decision highlighted ongoing discussions about access and participation in scientific fields. The Nobel Prize remains unchanged. It reflects the conventions and priorities of scientific recognition in the early 1970s. Bell's later honors reflect evolving perspectives on contribution and credit. Both are part of the historical record. The discovery of pulsars illustrates how science advances. It shows how careful observation reveals unexpected phenomena, how anomalies become new categories, and how recognition is shaped by institutional structure as well as discovery. Jocelyn Bell Burnell identified one of the most important astronomical phenomena of the 20th century. The Nobel Prize went elsewhere. The history includes both facts. If this made you pause, you might want to follow.